to retransmit data that went bad. I mean, what are we going to do? Put the listener's brain on hold while we wait to retransmit that piece of the video picture that was missing? No. So when we're doing things like voice over IP and video over IP, we don't use TCP. That's for file transfers. There's another protocol that's used, which is called UDP, the User Datagram Protocol. And UDP does sequence numbers and error checks, but it doesn't do retransmits. And this is used to provide a best efforts communication service across an IP network. Now, as we're going to see when we start talking about voice quality, the biggest problem is delays and variability in delay. And when we start looking at problems of packets going different ways or having variable congestion from 1 millisecond to another across a network, and so things take slightly longer or shorter to get to the other end, when we start trying to reconstruct this, you can imagine that if we took a coded version of what I'm saying right now and compressed it down into little chunks and sent them out on a regular basis, but they didn't arrive all exactly at a regular basis, the time between them was variable. If we started reconstructing that without fixing it, then we're going to hear all sorts of weird stuff happening. In some places there would be no information, and so we would just hear a click and silence and then a click while the sound started again. We're going to have a way of fixing this variability of delay of the packets arriving at the far end. The mechanism that we use to give us something to work with here is called RTP, the Real-Time Transport Protocol. And this does a number of things, including packet loss information and media content type, and it can do encryption, and it does segmentation. But the key thing it does for us is it puts a timestamp on every chunk of digitized speech and an identification of what the reference for the timestamp is. So the way it works is that we take the speech and put it through a codec, which does the analog digital conversion, and then we code that into whatever standard we're using to represent the voice, and then we take chunks of that or segments of that and give them to the RTP software. That puts a timestamp on the chunk of speech to say when it happened. Then we give that to the UDP software that puts a sequence number and error check on it. We give that to the IP software that puts the IP address of the far end telephone on the front of the IP packet. And then we put that inside a LAN frame, and we put the LAN card address of where we're going next, which is probably the router or the soft switch, on the front of the LAN frame, and then send it off over the LAN. And eventually, when it gets delivered to the far end, we pull in the LAN frame, check the LAN card address, pull the IP packet out of there, look at the IP address, and we see it's ours, so that means we're at the far end. So we pull the data out of there and give it to the UDP software that does some minimal error recovery with sequence numbers and error checks. And we take the data out of that and give it to the RTP software. And we use this in conjunction with something we're going to see is called a jitter buffer to then correct the timing before we do the digital to analog conversion to try to reconstruct the analog and hence the sound pressure waves in the best way possible. Just a few details of some things on this slide. We carry IP packets in frames, and inside the building they're going to be in Ethernet LAN frames. On wide area networks, they might be carried in ATM cells, or we might come up with some sneaky method of packaging all of the IP packets directly into a SONET frame. Sometimes what we end up doing is taking the IP packet in an Ethernet frame and then chopping that up and actually carrying them in ATM cells and then putting those inside SONET frames to carry them over a physical transmission network. The overhead starts adding up pretty quickly in this story. Speaking of overhead, at the top of the diagram we've got a little graphical representation of how the overhead gets added from what we can see inside the building. where we've got the payload, which is a chunk of coded digitized speech, and it's usually about 20 milliseconds worth of speech. And then the RTP protocol adds some control information onto that. Then the UDP protocol adds some more. Then the IP protocol adds some more information. And then finally the LAN protocol adds some more information as well. So we have a little nut of compressed digitized speech with a whole bunch of control information sitting at the front of it. In the H.323 world, we use H.225 call setup and H.245 capability negotiation. And there are a couple of pieces of jargon and buzzwords we have to cover here. When we want to communicate across an IP network, we're communicating from one software application to another. And we all know that when we have an IP connection through an internet service provider setup, you can have more than one application running. Like you could have your browser running and your email program running over the same IP protocol stack. So when a packet comes in, how does your computer know whether to give this packet to your browser or to your email program? Well, the way that that's done is that every application has a number, and this is called its port number. Like your browser is port number 80 or application number 80. Your email program is application number 25. File transfers is application number 20. So each application has an application number or a port number, and at the top of the TCP or UDP header, it's tagged right there saying what application this is intended for. So that's how your computer knows where to direct the contents of these packets. It looks at the front and it says, oh, well, this is for application number 80. So it puts in a little piece of memory space for application number 80. And application number 80, the browser is always checking to see if there's something new there for it. So when we want to communicate between two applications, we have to know not just the IP address of the foreign telephone, we also have to know what application number it is, what port number it is. And those two things concatenated together in the internet world, that's called a socket, the port number and the IP address. In the H.323 world, it's called a transport address. In any case, what it is a unique identification of the particular application we want to talk to. Now, to get back to our story here, in the H.323 view of the world, the way it happens is at first we have to open a TCP connection between the two terminals. And once that's all set up, we have a reliable communication channel between those two terminals. The next thing that happens is that we exchange what the H.245 transport address is. Remember, H.245 is capability negotiation. So to get started, once we can talk to the general processing application on the far end telephone, the next thing we need to know is what is the actual address of this piece of software that's going to do the capability negotiation. And once we exchange that information back and forth, then we open up a new TCP connection to do the capability negotiation. And this would be where one telephone says to the other, well, I'm a video phone and I want to communicate using H.261 video plus the G711 codec for the audio. What do you think of that? And another one would come back and say, well, I'm just an audio phone. We could use G.711 or we could do something more clever, which of course we're going to talk about as we get deeper into this subject. Once they have agreed on the format of the media and what kind of media and the standards and protocols are going to be used for actually doing the media exchange between the two phones, then the next thing we need to know is what is the exact address of the piece of software that's going to be sending and receiving the media back and forth. So we'll exchange that. Now, once that's all done, then we close all of these TCP connections. Remember, TCP does reliable communication. So we use TCP to do all of this setup information. Once we've got it done, we close the TCP, and then we use UDP to actually exchange chunks